Hello, this is Math Jazz from Almost Cool, and I have a live stream this week. It's been 2 weeks since my last live stream, but I have lots of questions to go over today. So, first question we have is a partial fraction decomposition question. So, uh, we're not going to do the full partial fraction decomposition because we've done that in a previous show, but just a quiz of how to find the general form for this rational function. So we notice on the bottom that we have a factor that is not completely factored. This x squared minus 4 is not completely factored into irreducibles, so we have to factor that. And since that term is squared, we're going to get, when we factor this difference of squares, x squared minus 4, we're going to get 2 of each of the linear factors. So we have x minus 2 squared and x plus 2 squared. And from here, we have one irreducible quadratic. We know this because, well, there are a few ways we can know this. One is that we have a square, which is positive, plus a positive number, and a positive plus a positive can't be 0. So there are no roots, so it can't factor. Or if we don't realize that, we can also notice that the discriminant of this is going to be negative. That is, in the quadratic formula where we have x is equal to negative b plus or minus the square root of b squared minus 4ac, that part under the radical b squared minus 4ac, b is 0, a is 1, and c is 3. So we have 0 minus 4 times 1 times 3, or negative 12. Negative 12 is negative. Negative discriminant means that we cannot factor this polynomial. We cannot factor this parabola. And everything else is linear, but some of the terms are repeated. So we'll have to take care of one irreducible quadratic and two repeated terms. This ends up being our general form. We have ax plus b over top of our irreducible quadratic. And then we have constants over each of our other terms, making sure that for repeated roots, we have both a single power and a second power for each of those. If we had had triple roots, that is, x minus a to the third, we would have to have, in the general form, a constant over first power, a constant over a second power, and a constant over a third. In general, whatever the power is, you're going to have to represent every natural number power up to and including the power that shows up in the factorization of the denominator. So, this is the answer, and we will move on. Problem 2. The lifetime of a particular processing chip is a random variable whose probability density function can be approximated by this function with time measured in years. We want to give an integral for the probability that a chip will fail within 4 years. That isn't a question, that's a statement. So, it's easy. The probability is going to be the integral from negative infinity to 4, but since the function is identically 0, that is, it is exactly 0 on the region from negative infinity to 0, then can delete that part of the integral. That part of the integral does not contribute to the value. So our integral from 0 to 4 of our function is all we need. Okay. Problem. We're going to find the centroid of this region bounded by these curves. Now, this will be a long one, but we can do it. We're going to first find where these curves intersect so we can get the limits of our integral. We notice that the two curves intersect at 1, 1, and so our integral is going to go from x is 1 to x is 3. All of our integrals are going to have those limits. We're going to find x bar first. Here is the formula for that. The A represents the area bounded by the region, or the area of the bounded region. So we're going to have to do an integral to compute that region's area. So to do that, we just take the integral of the difference of the two functions. Here are our two functions. We put x first because x is bigger than 1 over x on the region, on the interval that we're looking at. So this will give us a positive area. If you do it backwards and put the wrong function first, you'll get the same absolute value, but you'll have a negative sign. And so to fix that, you just switch the sign. It's no big deal. So we do this integral, and we get, well, it's a power rule on the x, and it's the natural log's derivative on the 1 over x, and plug in our endpoints, and we get an area. And fairly certain that's the right area. Now that we have the area, we can plug that into our original formula for x bar. We get 1 over the area times the integral of x times the difference of the two functions that bound our region. We multiply through, we use the power rule on each chunk, and then we plug in our endpoints and simplify. This represents our x bar. Now we have to figure out what our y bar is. And y bar is going to be a different formula. Notice, our x bar formula looked like this. It was x times the difference of f and g as the integrand. The y formula looks like this. Notice, instead of having an x, we don't have an x times the difference. We have the difference of the squares of our two functions, our two bounding functions, instead of having x times the difference of our bounding functions. And we have a half. Instead of 1 over the area, it's 1 over 2 times the area. So they're similar but subtly different. So now we already have the area, so we can just plug that in. And we know both of our functions, so we can plug those in and square them. From here, we just use the power rule. We plug in our endpoints, and we simplify. And this is our y bar, 10 over 8 minus 2 natural log of 3. So the centroid is just x bar comma y bar. Oh, we have people in chat. Hello to everyone in chat. And if you have any questions, I am watching my email address. That's mathjazz9@gmail.com. I should probably put those at the tops of the slides or someplace where people can see as they come in to watch. Okay, so that's problem 3. Let's move to problem 4. We're going to find the antiderivative of x times secant x times tangent x with respect to x. This is a bit of a tricky one, but we can do this with integration by parts. So we're going to let u equal x because that'll go away when we take a derivative, and that's great. It'll just be a constant. And we're going to let dv equal secant x tangent x because we know that secant x tangent x is the derivative of secant x. So we get du and v and we plug those into our integration by parts formula, like so. And we know that the integral of secant of x is going to be the natural log of the tangent of x plus the secant of x. Thank you for putting the email in the chat. Okay, so now that we have this, well, we're done. That's the answer. So we can move on. Okay, so now we have to find the integral from 0 to 1 of this fraction. And this goes back to our u substitution. It's not too bad. But we use u equals e to the x. I guess you could use e to the 2x. That might work. I think this is the easier way, though. And I didn't try the other substitution. You can feel free to give that a shot on your own. So we do our u substitution. We remember to change our endpoints for our integral. And we recognize, oh, this is the derivative of arctangent. So we get this is equal to arctangent of u from 1 to e. And we plug in our endpoints. And I simplified arctangent of 1 into pi over 4, but it's probably not necessary. So that's not too bad. Problem 6. What's the error bound for the midpoint approximation of this integral with this many with 10 subintervals if we know that the second derivative is less than 6 on the interval from 1 to 5? Well, we'd have to know the error bound for the midpoint approximation, which we do. It's going to be the absolute value of the cube of the length of the interval of integration times a bound on the absolute value of the second derivative divided by 24 times the square of the number of subintervals. And we know all of these values, I think, so let's plug them all in. We know that f double prime was less than 6, so we stick 6 into our k. And then we have 5 minus 1 is 4, so we have 4 cubed times 6 on the top, and 24 times 10 squared on the bottom. And we can simplify that a bit. We get the error bound is going to be 4/25. We have another approximation question. Suppose that f is a function with second derivative having absolute value less than 4 on the interval from 1 to 7. If we use the midpoint approximation to approximate the integral from 1 to 7, what is the smallest number of subintervals we can use to ensure that the approximation is within 1/100th of the actual integral? So this has ready applications into engineering and science. There are several times where we know that we can't get an exact result, but we want to know how precise do we have to be to get within the error that we desire. In this case, we want to be within 1/100th of the actual value. How precise do we have to be? Well, it's going to require lots and lots of rectangles. But this is how we set this up. Here's our formula for the error bound on the midpoint approximation. We know that b minus a is 6, k is 4, we're solving for n, and we want the error to be 1/100th. So we plug those in and we get this equation. From here, we solve for n squared. So multiply both sides by n squared and cancel out at 24 on the top and bottom of the right fraction. Multiply both sides by 100. it all comes out to be, there's an extra square here. This square shouldn't be there. It's 6 squared times 100, which gives us 3,600. Okay, so problem number 8. If we have this curve, which is a line with slope 2, passing through the origin, if it's rotated about the y-axis, what's the surface area? Again, if we're only rotating the chunk between x is 0 and x is 3. Well, you have to remember what the surface area formula is. And here it is. When we're rotating around the y-axis, we do x times the square root of 1 plus the derivative of the function. When we're rotating around the x-axis, we do the function times the square root of 1 plus the square of the derivative of the function. So we have this integral, and it turns out to be not so bad. Derivative of 2x is 2. That makes everything under the square root a constant, which is great. Integrate x, which is easy. Now we plug in the endpoints, which isn't so bad. So that's pretty good, pretty easy. Okay, question 9. Which of the following improper integrals converge? So we have 4 integrals here, and we want to figure out which of these converge and which of them diverge. So we're going to do these one at a time. Here is A. So when x is large, x to the 7th is going to dominate the other terms in the polynomial. So we know that x to the 7th is going to be less than 3x to the 7th minus x squared minus 9. Is eventually the x squared and the 9 really don't matter. But if we know that, then we also know the square root of x to the 7th is less than the square root of this polynomial. And we're going to take the square root of x to the 7th. That's x to the 3rd times x to the 3rd times x. And so the square root of x to the 3rd times x to the 3rd is just x to the 3rd. So we get that x to the 3rd times the square root of x is less than our square root of our polynomial. And this is the important part, because then if the denominator of this fraction is bigger than the denominator of this fraction, and the two numerators are equal, then this fraction is less than this fraction. And this fraction, we can cancel out the x squared from the top and the bottom. We get 1 over x to the 3 halves. So we now know that the integral that we want is less than an integral that we know converges, because the integral from some constant to infinity of 1 over x to a power, where that power is bigger than 1, is always convergent. Say that one more time. If we have an integral, it goes from a constant to infinity of 1 over x to a power, and that power is bigger than 1, then this integral converges. If the power is smaller than 1 in this denominator, then we know it diverges. And if it's exactly 1, it's going to diverge as well. Okay, so we have this, and that tells us that the first of the 4 integrals we're looking at converges. So we're going to go on to the next one. Here is 9b. We're going to check to see that this integral converges, or maybe we're going to show it diverges. Well, it looks like x to the fourth minus 1 is less than x to the fourth, because if you take 1 away from something, it gets smaller. So the square root is going to be less than the square root of x to the fourth. The square root of x to the fourth is x squared, so this fraction is going to have a smaller denominator than this fraction, so this is going to be a bigger fraction than this one is. If this fraction is bigger than this one, and this one equals 1 over x, and 1 over x diverges, this integral will diverge, because the integrand is bigger than the integrand of an integral that diverges. Okay, so we have here another integral, and we have to figure out if this converges or diverges. So we're going to do a u substitution. Using our u substitution, we're going to get this power. We use the power rule on it. We get the limit as b goes to 0 of 1 over negative 1 over u from negative 10 to b. But the limit as b goes to 0 of negative 1 over b is infinite, so that's going to diverge. So since this limit diverges, this whole integral diverges. Whole thing diverges. Okay, so let's look at the next one. So this is the same kind of idea. 1 minus x squared is bigger than negative x squared, because if you add 1 to something, it gets bigger. Since this is a bigger denominator, this fraction is smaller than that fraction. And this x over negative x squared is just negative 1 over x. That diverges to negative infinity. The fraction we were given is less than a fraction that diverges to negative infinity. So it's also going to diverge to negative infinity. Okay, so that gives us problem 9. Problem 10. We want to give an integral representing the arc length of this curve on this interval. So that's not too bad. We use the arc length formula. It's going to be the integral from 0 to pi over 4 of our function, which is sine x, times the square root of, wait, this is wrong. Sorry, scratch the sine x. It's the integral from 0 to pi over 4 of the square root of 1 plus the square of the derivative of our function. So I can't cancel out the x there, but you'll have to do it on your own. Okay, so that's not too bad either. Problem 11. So we have a probability density function. This probability density function is given as stated. We want to know what value of c makes this a probability density function. Well, the first thing to note is that we need to make the integral of p of x from negative infinity to infinity equal 1. We need the area under the curve to be 1, so that means that we need to take this integral from negative infinity to infinity, but we notice that since the function is equal to 0 when x is less than 0 or greater than 2, those parts of the integral don't matter. So we just integrate from 0 to 2, and we get our antiderivative using the power rule. We just multiply everything out and use the power rule. From there, we plug in our endpoints, and we simplify. And we get that the area under the curve is 4/3 of c. Well, we want this area to equal 1, so c has to equal 3/4 for that to happen. So C is 3/4. Okay, so if C is 3/4, then we can update our probability function by plugging C in and multiplying everything out. And I think I did that right. Sure, someone can correct me if I didn't multiply correctly. Part B of our question was find the median. Well, the definition... Oh, actually, we're going to cheat. I'll get the definition at the end. But what we notice is that this is symmetric. This is a parabola, so it has a vertical axis of symmetry. The left side is a mirror image of the right. And whenever you get symmetry on a median, when trying to find the median has to land on the axis of symmetry. So, and this actually holds true for finding centroids as well. If there's some sort of reflective symmetry when trying to find a centroid, the centroid must lie on the reflective axis. So that's a really nice tool to know if you see if you're given a centroid problem and you recognize, oh, this has got some sort of symmetry, you automatically know one of the coordinates of your centroid. And it's perfectly legitimate to do that on an exam. If you can prove that your function is in fact symmetric somewhere, then you can it's easy, and the grader's actually probably expecting you to do that. Anyway, getting back to this problem, we're going to cheat. We have a polynomial. So the median is going to be the x-coordinate of the vertex. The vertex is at negative b over 2a, or the x-coordinate of the vertex is negative b over 2a. Plug that in, we get 1 as our answer. Also, the other, which I think is easier but might not be as intuitive, is that the vertex always lies halfway between the two roots. The x-coordinate of the vertex is always going to be just halfway between the two roots. Since we know that one of the roots is at 2 and the other root is at 0, halfway between them is 1. That's another way of doing that. We have a question in chat. Oh, well, we have question marks in chat. Okay, so we will move on to part C of the problem, which was to find the mean of the problem. Oh, and I did promise I would show you the formula for median. Here's the formula for median. It's the integral from negative infinity to m of the function. Well, let me start over. The formula for median is the integral from negative infinity to, no, one more time. The median is the number m such that the following equation is true. The integral from negative infinity to m of your probability density equals 1/2. In our case, since our probability density is 0 when x is less than 0, we just have to integrate from 0 to m and set it equal to 1/2. Whatever number m makes this statement true will be our median. So, and then we'll move on to the next question. Calculate the mean. The mean is not too bad either, actually. The formula for the mean of a probability function is x bar equals negative infinity to infinity of xf of x dx. It's this integral. It turns out this is, if you recognize it, it's actually the same x bar formula as for a centroid. So that's kind of cute. So, and by symmetry, your mean is going to end up being the same as your median. So we know it's going to be 1, but we might as well do the integral just for the practice. So we integrate from 0 to 2 the function x times our probability density. We get this integral. We use the power rule on each chunk. We plug in our endpoints, and we get 1, which is exactly what we expected. So that's not too bad either. It's just extra words for concepts that we've already learned. So it's not too bad. Maybe setting up the integral is something to review before the exam. Problem 12. We're going to determine the value of this integral, which is the integral from pi over 4 to pi over 2 of the function cosine theta divided by the third root of sine theta with respect to theta. So we're going to do a u substitution. We let u equal sine theta. It gives du equals cosine theta d theta. Plug that into our integral, remembering to change the limits of the integral. And after that, it's just the power rule. There's the power rule. Here we plug in our endpoints. And I simplified a little. So that's not too bad either. Here is problem 13. So this one we look at and we think we want to do integration by parts. So we first have to factor the denominator, and then we set up the general form of the partial fraction decomposition, like so. And we need to figure out what a and b are. So we multiply by the denominator of the left-hand side of the equation, get this. We plug in 1 to kill off the a term. We get b is 1. We plug in 0 to kill off the b term and get a is -1. From here, we plug both of those into our partial fraction decomposition, and we integrate that, get the integral from 0 to 1 of -1 over x dx, plus the integral from 0 to 1 over x minus 1 dx. And from here, we notice that the left integral doesn't exist. And this means that the whole thing doesn't exist. So this diverges, and we're done. So now we're getting into our integral approximation techniques. Here's a table. It represents a function, and we're going to take an integral of it. We're going to use the trapezoid rule to approximate, and we're also going to have to use Simpson's rule to approximate. And I did not mean for these numbers to come up here, but since they're here, we might as well take a look at them. This is the trapezoid rule approximation. We have 1/2 because 1 is the width of our rectangle, and our trapezoid rule is 1/2 times the width of the rectangle times our sum of heights. We have 1 times the first value plus 2 times all of the values up until the last one, and 1 times the last value. So this is because we're basically averaging the height at each endpoint of a rectangle to get our trapezoid. And so we get delta over 2, which is 1/2, times the first height plus 2 times the second height to the second to last height plus the last height. So That's 1/2 times 5 plus 20 plus 22 plus 26 plus 12. And let's see what happens. That's 42.5. I think that it's going to go into the Simpsons rule next, but the slide is scaring me because it didn't quite load properly. Here's our Simpsons rule. Okay, so we have our Simpsons rule is going to be 1/3 times the width of the rectangle times our sum of heights. Now the Simpsons rule is going to be the first height plus 4 times the second height plus 2 times the third height, alternating 2s and 4s until we get to the end, where the second to last term will be 4 times a height, and the last term will be 1 times a height. And so that's a pattern that you'll have to feel comfortable reproducing. That said, we have 1/3 times 5 plus 4 times 10 plus 2 times 11 plus 4 times 13 plus 12. That is our Simpsons approximation. And that gives us this sum when I multiply these terms together. And when I add all of those terms, we get 131/3, which I guess is 40. What's that? 43 2/3, I think. Which is pretty close to 42.5. This is probably going to be more accurate because, in general, the Simpsons rule is more accurate than the trapezoid rule would be. If you have the same number of rectangles, it's usually more accurate. Okay, so problem 15. A trough has ends that are in the shape of a right isosceles triangle with one of the legs horizontal and the other vertical. If the legs of the isosceles triangle are 1 meter long, the trough is full, find the force due to fluid pressure on one of the triangular ends. The weight density of the liquid is rho g. Okay, so here is a diagram that represents that information. Always draw diagrams for these problems. So this has a lot of information on it, but what we need to find out what is the force on a differential rectangle at a depth of x. It's a lot of setup that needs to be done, but first we go down a depth of x and we have to figure out how wide are the rectangles at that depth for this object. Well, fortunately, this triangle has a 1:1 ratio between the side and the base. So that means if I go down x, the distance across is also x. So that's the first thing we know. We know that the width of this rectangle is x. The height of the rectangle is dx. So we have our differential area element, which is x dx. What remains is to find what is the pressure exerted against that x dx rectangle. Well, it's going to be 1 cubic meter of the fluid times the density of the fluid. Well, it's going to be 1 cubic volume element. In this case, it's meters because we're working in meters. But so since we're working in metric, it's 1 cubic meter because we're measuring everything in meters times the density of that meter times gravity times the depth. So the integral will look something like this. Rho is the density, g is gravity, x is the depth, times x dx is our area of our rectangle. We're integrating from 0 to 1. This is going to give us our hydrostatic force. If we were in the imperial system, then we'd be using differential feet sorry, we'd be using cubic feet as our to find the weight of the water on our differential rectangle. We wouldn't have to multiply by gravity because the imperial system does everything in pounds, which is a weight, not kilograms, which are a mass. So the only difference between the metric integral and the imperial integral is that the imperial integral will have the weight density rho times depth x, whereas the metric will have the mass density rho times gravity g times the depth x. So you'll have to remember that. We don't multiply by gravity in the imperial system. Okay, so we have this integral from 0 to 1 of rho g, which were not values we were given. So we'll leave them as constants, times x squared dx. And we use the power rule for that. We get rho g times a third of x cubed from 0 to 1. Plug in our endpoints, getting rho g over 3 as the hydrostatic force. So all we would need to know at this point is what rho is and what g is. If we were given those, we'd be able to figure out the force. So I have a few more questions that I'm not going to do because I ran out of time to tech them, but I'm going to show them to you anyway. Here's 16. We're going to find the length of this curve on that interval. This is very similar to the surface area integral that we did earlier. I think we also did an arc length integral earlier. So let's take a look at, I think it's right. It was further back than I thought. Here we go. So remember, there is an error. The sign of x shouldn't belong there. But the arc length is going to be the integral from one endpoint to the other of the square root of 1 plus the square of the derivative of your function. So using that on problem 16 would give us verbally the integral from 1 to e of the square root of 1 plus the square of the derivative of this function. So we take the derivative, then we square it. Can't square it and then take the derivative. That'll give a wrong function. I'm not going to do this problem, but you can take a look at it and feel ready for the exam on it. Here's another integral. This is also going to be integration by parts. We've already had 2 examples of that, so you can do that on your own. Here's a centroid question. We've already done one centroid question, and it's the same as the other centroid question, except that we're not even asking for both coordinates. We're only asking for y bar. Go over number 9 again. Okay. Let's see, number 9. Oh, there are lots of parts to 9. Okay, so when determining whether an integral converges or diverges, what's easiest to do most of the time is to compare to known integrals. If the absolute value of the integral you're looking at is bigger than the absolute value of a divergent integral, then you will you'll have a divergent integral. On the other hand, if the absolute value of your integral is less than the absolute value of a convergent integral, then your integral will converge. Basically, if you're smaller than a small thing, then you're small. So if you're less than a convergent integral, you're convergent. And if you're bigger than a big thing, then you're big. If you're bigger than a divergent integral, then you're divergent. Question, where did I get these practice problems? These were ones that came to me after looking at draft 2 of the exam this weekend. So that is where these problems came from. They were just things that I was thinking of after reading through the last draft of the exam. General form for the pressure problems. I think that the best way to answer that is to go back to this. So here's the general form of a pressure problem for a metric problem. Density times gravity times depth times your differential area, which is going to take the form of some rectangle. You're going to have to figure out a formula that gives you the width of the rectangle at the depth of the rectangle. So that's the general form of a pressure problem. On the other hand, since I said this is the metric form, the imperial form is just density times your depth times your volume element. You don't need to multiply by gravity because what we call density in the imperial system is weight density, not mass density. So, looking at this form here, the form for a standard integral or an imperial integral for hydrostatic force is going to be rho x times your differential area. Okay, let's see if I'm caught up with chat questions. Lots of jokes about Divergent and Insurgent. That's fun. I haven't read those books. I've been told that I would like them. Maybe I'll get to read them over Christmas. Looks like we are caught up for the chat questions. Let's see. We showed you 16, 17, 18 was the centroid question. 19, I think this is the last one that I teched up. Find the surface area of the solid obtained by rotating the region bounded by y equals 3x from x equals 0 to x equals 4 about the x-axis. So we did do a rotational surface area question already. I think we did that one around the y-axis. The thing to remember is that, and I'm going to just scroll back to our other, yes, here's our surface area. So when we're rotating around the y-axis, we have our surface area integral, which is the integral of the square root of 1 plus the square of the derivative. But we have to multiply that by 2 pi x because we're going to rotate that area around the y-axis. And so we treat x as the radius, and 2 pi times x gives us the circumference of the rotation. To rotate around the x-axis, it's the same idea. We need to have rotation around the x-axis, so our radius is going to be the height of the function rather than the x-coordinate. So we're going to have 2 pi times the integral of f of x times the square root of 1 plus the square of the derivative of f as our surface area integral. What sections does the test cover? I think chapter 8. I think everything after what we covered for the last exam up to the end of chapter 8. And did I help write the test? I submitted a question and it didn't make it into the last draft of the exam. So I don't even remember what my question was, but it wasn't accepted. So I was a little miffed for a day or two, but then I got over it. It was an approximation question. But the questions that I saw on the exam for integral approximation didn't seem harder than what I suggested. It was just they didn't use mine. Okay, so let's see, what next? I showed you all of our questions. Yes, all of the questions that I wrote for today I showed you. This isn't so bad. This should be 2 pi times the integral. Since we're rotating around the x-axis, we use our function of x. So it's 2 pi times the integral from 0 to 4 of 3x times the square root of 1 plus the derivative of this is 3, so 3 squared is 9. So it's the square root of 1 plus 9 with respect to x. And so that function is actually just the integral of a line, so that's not hard either. Any other questions? Are these questions a pretty good representation of the test? So the way that I started writing this review was I copied and pasted the questions from the exam into a Beamer document, and then I tweaked the wordings and numbers until I got this. Also, I added a few questions. I think I added 3 questions. So, yeah, I would say these are very representative of what I saw on draft 2 on Friday. And I guess they might have changed something from 8 in the morning until they submitted it at noon, but probably not a lot. Okay, other questions? If not, then I guess we will call it a day. Thanks for watching. I do this most Mondays. I took 2 weeks off, but I'll be back on the wagon this week and to the end of the semester, I hope. So, hope to see you next week, and have fun learning math. Bye!